Welcome students. So in this lecture series we will discuss of the course BSC 301 Mathematics 3 for third semester of Computer Science and Engineering Department under the colleges of Maulana Abul Kalam Azad University of Technology. This is a 2-credit course, but the syllabus is quite large, we can say. It has 5 modules. The first module discusses about sequences and series. Then module 2 and 3 revolves around multivariable calculus, and module 4 about ordinary differential equation, and the last, that is 5th module, it is an introductory graph theory part. So in today's lecture we will start with our discussion with sequences and series. So before going into the discussion of sequence and series, we should have a little bit knowledge about what is real line. So what is real line? Suppose we have a fixed distance. If we call or assume this distance to be unit distance, then the left end point we call this to be the real number 0 and the right end point to be the real number 1. Now, what will be its midpoint? Yes, of course, it will be half. Similarly, if we draw twice the length of this unit distance, then the end point will be 2. Its midpoint will be 1.5, that is 3 by 2, and so on. So in this way, the positive rational numbers will be plotted in this way, and if we go the same distance on the opposite direction, the unit distance, then it will be, the end point will be -1. In this way, there will be -2 and so on. So these are basically positive and negative rational numbers. Suppose we have to plot 1/3, then what will be it? So suppose we have a thread of unit length. If we can fold it to get a 2 times. So to get a 3-fold, number of total fold is 3, equal fold, then that much length will be 1/3. Say this is the 1/3. So these are rational numbers. Similarly, few irrational number we can also plot on this real line. Suppose we have to plot √2, then we know that √2 is nothing but length of the diagonal of unit square. So if we draw the unit square, then this much length, the length of this diagonal up to this much, this will be near 1.4. So this will be √2. Similarly, we can plot √3. So what I want to actually understand you that for each real number there is a unique point in this real line. By real number I am denoting all the complex numbers of which imaginary part is 0. So for each real number there is a unique point on this real line and vice versa. That means for each point on this line there exists a unique real number. That means there is a unknown correspondence among the real numbers and the points on this line. We call this line to be real line. Okay. So as we can see that negative numbers increase without any decreases without any bounds, and similarly positive numbers increases without any bounds. So this line is basically on the both sides it is infinitely extended. So now before going into the definition of a sequence, we need few more definitions of what is boundedness. So what is bounded below subset of R? R means, by R we are denoting all the numbers on the real line which we call to be real numbers. So a set S which is a subset of R is called bounded below if there exists a real number small m. This is the symbol for there exists. Such that this is the symbol for such that which is reflection of epsilon. Such that small m is less than equal to elements of S. That means small m is less than equal to a small s for all the elements small s in the set capital S. Such a n is called a lower bound. A lower bound of the set S. Okay. So what is the example? Suppose we have the set on half, on third, and so on. Call this set to be S1. Then we can see that all the elements in this set is non-negative, right? So that means without any ambiguity, what we can tell that 0 will be less than equal to S for all S belong to S1, because the elements of S looks like 1 by n, where n is a natural number, and we know that 1 by n is of course greater than equal to 0 for any n belongs to natural number. Okay. So this S looks like 1 by n for some natural number n. Natural number means whole positive numbers. So this 0 is a lower bound here. It is a lower bound here. Now someone else, instead of telling 0, someone can tell that minus 0.1 is also less than all the elements in the set S. Yes, that is also true. So this is also another lower bound. This is another lower bound. So that means once we have a lower bound of a set, then anything which is less than equal to that lower bound will also work as a lower bound, right? That means when a set is bounded below, although to show that a set is bounded below, we have to show that there exists at least one lower bound, but eventually it will consist of infinitely many lower bounds. So similar concept is available for bounded above set. So what is bounded above set? Or bounded above subset of R. So what is bounded above subset of R? So a set A subset of R is bounded above if there exists n belongs to R such that now all elements in the set S is less than equal to the real number capital A. And similarly, such a M will be called a upper bound of the set S. Okay. So take an example. Say we have the 1 by 2, 2 by 3, 3 by 4 and so on. Okay, and call this set to be S2. Now see, can you think of an upper bound for this set S2? Okay, probably you have guessed right. So see, what we can observe here, that the elements of the sets are of the form n by n plus 1. That means both numerator and denominators are natural number, but denominator is 1 more than the numerator. That means its value is less than or equal to 1, right? Or in other words, that is small s less than or equal to 1 for all s belongs to S, because elements of this S2 are of the form n by n plus 1, where n is a natural number, right? So this one works as an upper bound here. So anything greater than or equal to 1, that will also work as an upper bound, which is quite obvious. Okay. So from here, now we will define what is bounded subset of R. What is bounded subset of R? So which is both bounded below as well as bounded above. So a set S subset of R is called bounded if it is both bounded below as well as bounded above. Now analytically what we can tell? Analytically, S is bounded above if there exists capital M greater than 0 such that mod of S, or absolute value of elements of the set S, is less than or equal to n for all S belongs to S, which in other words turns out that elements of S are range bound in between minus n and n. Okay. So if this thing happens, then we call the set to be bounded set. So what is an example? So you can think of this set. Say the set is simply S1 union S2. The previous S1 and S2, which turns out to be on third, on half, and this side we have on fourth and so on. Then 1, 2 by 3, 3 by 4 and so on. Okay, and call that set to be S3. Then we already know that on will also work as an upper bound for this set, because all the elements of this set are less than or equal to 1. And similarly 0 will work as a lower bound, because all the elements of the sets are positive as a lower bound. Now my question is, what will be this aim for such a set? Okay. So what you do? So you have found out the upper bound to be 1. and lower bound to be 0, take their absolute value. So absolute value of 1 is 1, absolute value of 0 is, this was lower bound and this was upper bound. This is 0. Take their maximum. So maximum of 0 and 1 is 1. So this 1 will work as a m in this definition. So what we can see that minus 1 less than equal to s less than equal to 1 for all s belongs to S3. Here S3 is a bounded set. I think the idea is clear. What is bounded set? See, so in fact a set will be bounded if you can find out two real numbers small m and capital M both belongs to R such that m less than equal to s less than equal to m. Okay, here m will be a lower bound and capital M will be an upper bound, but from this definition we can conclude this definition by taking absolute value call this m dash or this small m dash by taking m to be the max of m dash and capital M dash. Okay, so from this definition the original definition of bounded set will follow. So basically all, if the concept is clear to you, then it is the same thing, nothing different than this. Okay, so now we have the concept of what is bounded subset of R. Now we will get into the concept of what is greatest lower bound and least upper bound. So as you can see in this example that the set S1 has a lower bound 0. Okay, now anything which is lower than 0 will also work as a lower bound, that is quite obvious. But my question is it possible that there is anything greater than 0 which will work as a lower bound for the set S1? Think few seconds. So I think you are not getting any answer, right? Because anything which is lower than 0, if you think greater than 0, if you think say 0.001. Now see, this will not work as a lower bound. Why? Because its value is nothing but 1 by 1000, but there is 1 by 1000 on in the set. There is 1 by 1000 on in the set, and here on upon 1000 is greater than equal to 1 upon 1000 on. So this phase 2 works as a lower bound, right? So that means in case of lower bound we are often concerned about what is the greatest lower bound, right? Because once we obtain the greatest lower bound, then all the lower bound will be known, because anything which is lower than that greatest lower bound will work as a lower bound. So this lower bound, which is greatest among all possible lower bounds, will be called greatest lower bound. And similar concept will be available for least upper bound, which will give formal definition. So what is greatest lower bound? It has another name which is infima. symbolically we will denote by GLB, greatest lower bound. So for a bounded below set S, small m is called greatest lower bound of S if these two conditions are satisfied. What is the first condition? M is a lower bound of S, and condition number 2, M is greatest among all lower bounds of S. Okay. So it has one more analytical definition. So before going into the analytical definition, first get through the example clearly. So we will consider the same example which we have taken on half, on third, and so on. This is our set which was S1. Okay. Now see, since everything are positive, so irrespective of thinking or going into detail of the elements of the set, we can directly tell that 0 is less than equal to small s for all small s belongs to S1. So 0 is a lower bound. The first criteria is satisfied. Now M is greatest. To satisfy the second criteria, that M is greatest among all lower bounds of S, consider anything greater than 0 and check whether it is possible for that element to be a lower bound or not. Or in other words, to show that 0 is the greatest lower bound, we will show that anything greater than 0 fails to be a lower bound. Right? The same thing. So that will assure that means 0 is the greatest lower bound. So take anything very small amount we are increasing from 0. Say 0 plus 10 to the power minus 10, which is in fact 10 to the power minus 10. Okay. Now see, we have 1 by 10 to the power 10, which is a natural number, plus 1. It is a member of our set S1, right? And this is and 10 to the power minus 10 is what? 1 by 10 to the power 10. So this is less than 1 by 10 to the power 10. Since 10 to the power 10 plus 1 is greater than 10 to the power 10, so its reciprocal, for its reciprocal, the inequality sign will inverse. So what it means? That now this 1 by 10 to the power 10 is no more a lower bound, because for lower bound it has to be less than equal to all the members of the set, but we have obtained a member which is belongs to this S1 and it is less than 1 by 10 to the power 10. That means this 1 by 10 to the power 10 or 10 to the power minus 10, it fails to be a lower bound. So anything, if you increase from 0, it will fail to be a lower bound of this set S1, hence 0 is the greatest lower bound. Okay. So now we will go into the analytical definition of greatest lower bound. So what is analytical definition? So for a set A subset of R, small m is greatest lower bound, or we also call it as infimum of S if the first condition is that m has to be a lower bound. That means small m is less than or equal to S for all S belongs to S, and for any epsilon greater than 0, and this is for second condition. Okay, for any epsilon greater than 0, epsilon is a positive number, but it can be any positive number, however small it may be, but once chosen it is fixed. For any epsilon greater than 0, m plus epsilon fails to be a lower bound. That is, there exists S dash, a member of the set S, such that S dash becomes lower than m plus epsilon, which makes m plus epsilon impossible to be a lower bound. That means m plus epsilon fails to be a lower bound, right? As in the previous case, you can consider here 10 to the power minus 10 as epsilon. Once we have chosen, we obtain an element S dash. In this case, S dash is, this is our S dash, 1 by 10 to the power 10 plus 1, which is a member of the set S1. So if these two criteria are satisfied, then we can assert that this small m is the greatest lower bound or infimum of the set S. So similarly, we have the concept of least upper bound, or supremum. It has another name, supremum of a bounded above set. So what is supremum of a bounded above set? So we are directly going into the analytical definition. Basically, as the name suggests, least upper bound. So for a bounded above set, we know that it has an upper bound. So among all the upper bounds, whichever will be the lowest, that will be called least upper bound. Because once we know the least upper bound, that means that we know all the upper bounds. Because anything greater than that least upper bound will work as an upper bound. So we are mainly concerned about the lowest among all the upper bounds. Okay. So we are directly going into the analytical definition. So for a bounded above set S, M is supremum or least upper bound, same thing, of S. Of course, S is subset of R if first condition is what? Capital N is an upper bound, that means S is less than or equal to N for all s belongs to S, and for any epsilon greater than 0, m minus epsilon fails to be a upper bound. Because if this happens, that means what? M is the least possible upper bound. If we less however small from M, then it fails to be an upper bound. That means what? M is the least upper bound, least possible upper bound. So it fails to be upper bound, that is, there exists S dash belongs to S such that M minus epsilon will be less than S dash, and it will assure that M minus epsilon is no more a upper bound. Okay. So here we can punch the fact that S less than equal to M, so it will be less than equal to M, that means less than M plus epsilon, because epsilon greater than 0, and similar punch we can also do in case of greatest lower bound. S dash was M was less than equal to S dash, so that means it will be less than M minus epsilon. Okay. So let us give an example here also. So we will take the same example here. Half on third, half to third, 3 by 4, 4 upon 5, and so on. Call the set to be S2. Here we can see that the elements of the set are of the form n by n plus 1, which is of course less than equal to 1 for all n belongs to the set of natural number n. That means small s less than equal to 1 for all s belongs to S, because elements of S2 are of the form n by n plus 1. Okay. So this 1 works as an upper bound. Now we will show that this 1 is the least possible upper bound. So suppose we want to subtract or less this 1 a little bit, okay, and check whether it is still an upper bound or not. So say suppose we are considering 0.99, which is actually 1 minus 0.01. So we are lowering the value of the upper bound 1 by a small number 0.01, and we obtain 0.99, which is actually 99 by 100. But we have in the set 100 upon 101, and you can check that 99 by 100 is less than 100 upon 101. Okay. You can check this fact. Simply multiply 100 square. It will be greater than 99 into 101. So this result will hold. Okay. So suppose someone is thinking that we have lowered a very high number. If we have lowered a little bit less, then it could be possible. So suppose we are lowering 0.001, which is 0.999, which is 999 upon 1000, which is again lower than 1000 upon 1001, which is also a member of the set S2. This belongs to S2. This belongs to S2. Okay. These are also belongs to S2. That is not our concern. What we want to tell that this 0.99 is not an upper bound, because we got an element in S2 which is greater than 0.99. Similarly, 0.999 is also not an upper bound. That means what? However small we are lowering from 1, it is failing to be an upper bound. That means 1 is the least possible upper bound, which we call least upper bound or suprema. Okay. So I think the idea is clear.